Okay, good evening, everyone. Welcome to the second of our nuclear masterclass webinars. It's great to see so many of you joining us live. My name is Dr. Josie Rawes, and I'm a physicist at the University of York. A couple of housekeeping bits before we get started. If you would like subtitles, you can turn these on using the CC or Show Captions button on your screen. And if you have any Wi-Fi issues throughout the session, you can rejoin the webinar using the same link you've already used. And please note that this webinar is being recorded and will be shared with all ticket holders and on the Nuclear Masterclass webpage earlier next week. You can submit questions at any time throughout this evening's event via the Q&A button at the bottom of your screen, and I'll put as many of these questions as possible to our speaker at the end of her talk. Okay, and so to this evening's event. Tonight we're going to be finding out about the what, why, and how of particle physics. So we're going to be joined by Dr. Kate Pachel, who is an experimental particle physicist whose research focuses on searches for new particles. She's been a member of the Atlas collaboration for more than 10 years, but has recently turned her focus to developing the DarkLight experiment. She got her BSc from the University of Victoria and her PhD from the University of Oxford, and she worked as a postdoc first at Simon Fraser University and then at Duke University before beginning her current position as a research scientist at TRIUMF. So without further ado, I'm going to hand over to Kate to teach us about particle physics.
All right, thanks so much, Josie. It's a real pleasure to be here, getting to talk to all of you today. So yes, welcome. I'm very excited to get to talk to you about particle physics. Now, my understanding is that this is really a sort of nuclear physics oriented course that you're participating in here. So I'm excited to get a chance to tell you about something very closely related, but that does have a few differences. So let's get into what those might be. There really isn't a sharp line between particle and nuclear physics. I'll start out by saying this. The two are very, very interconnected. But in general, if I were to try to define where the differences lie, I would say that particle physics is concerned with the properties of fundamental particles or composite particles, rather than with emergent properties of groups of particles. So one way that we could think about that would be by looking at a nucleus. So the properties of nuclei, that is groups of protons and neutrons, and the emergent properties that come from putting all of them together in these groups, that's very much the realm of nuclear physics. Taking one of those individual protons or one of those individual neutrons and studying its properties, that's really on this line. That's something that would fit into both camps, and we have nuclear and particle physicists studying protons in their various behaviors and various sort of types of interactions they might have. If we were to look inside of the proton, we would see that it is not a fundamental particle. It is, in fact, a composite particle, and it's made up of fundamental particles called quarks. And studying the properties of those quarks, that fits into the realm of particle physics. So again, though there is overlap, there are these differences as well, but the two are very often grouped together. So it's fun to be able to talk about this with you here. Now, the next thing I want to discuss is why this is often related to an energy scale. You will sometimes see particle physics referred to as high energy physics. What's that about? Let's start by thinking about how we observe stuff with light. So if you're looking at an object, what you're seeing is rays of light scattering off of that object and coming back to your eyes. And we can see an object with light as long as the size of that object is larger than or comparable to the wavelength of the light. So I'm going to use this nice diagram that I got off of the internet. Thank you to the user who made this. What you're seeing here is essentially an image showing that across the spectrum of light, we go from light with very long wavelength, that's the distance between the peaks, to light with very short wavelength. Long wavelength is lower energy, short wavelength is higher energy. And what you would be able to see with light of that wavelength depends on that size. So the visible spectrum is generally light in the area of around 350 nanometers to around 700 nanometers in wavelength, which means that about the smallest things we can see with visible light are single cells. We can't see those with our naked eye, but you can see them with a microscope. You can take a microscope, you can scatter light off of a cell, and you can look at it and see it. But you can't see individual molecules with a regular visible light microscope because they're smaller than the wavelength. And so when light hits them, it'll just kind of bend around them and it won't actually scatter back to your eyes. Because small wavelength corresponds to high energy, it means that if we want to see smaller things, we have to go to higher energy probes to be able to actually essentially interact with those objects. So as we were seeing there, the very highest energy gamma rays, those have very small wavelength and you might be able to probe nuclei with them. What if we want to study something smaller than a nucleus? So this is where we're going to turn to something I'm not going to talk about in great detail here, which is the concept of particle-wave duality. So all I'm really going to say is that a particle can correspond directly to a wave with a specific wavelength. And the relationship between the particle and the wavelength is through the particle's momentum with this very simple equation right here. So P in this equation, that's going to be the momentum of a particle. H here, that's Planck's constant. It's just a number. Doesn't really matter what it is. It's just a number. And this lambda over here, this is wavelength. So this is the wavelength of the wave that this particle corresponds to. So if you want to get something with a small wavelength, you would need a particle with a big momentum, and that would be equivalent. So let's go back to thinking about how you could study an atom. If an atom has a width of about 10 to the minus 10 meters, then we could rearrange this equation to solve for momentum, put in 10 to the minus 10 meters for a wavelength that we want, and we would find that you should be able to scatter off of an atom and measure something about its properties with a particle that has 10 to the 4 electron volts of energy. Again, electron volt is just a way that we tend to measure energy or momentum for a particle. Don't worry too much about what it is. The main thing here is that that scale is not super high for us. So achieving 10 to the 4 electron volts of energy for an electron is something we can do in electron microscopes. So you can use an electron microscope to fire a beam of electrons at a material and look at what scatters back and use that to form an image. And because these microscopes work in the sort of 10 to 100,000 electron volt energy range, we can use them to make pictures of atoms. But okay, what if we want to look at a nucleus or a proton or inside of a proton? So we can do the same math here. We can say that if we want to probe something on a distance scale of around 10 to the minus 15 meters, so more like the size of a proton, we would need to do that with a particle that has at least 10 to the 9 electron volts of energy, or what we would call a giga electron volt. And that's starting to get pretty serious. We're starting to get into the energy range where you really are going to have to work pretty hard to make that particle. So if we want to explore the properties of fundamental particles, it's going to require these very high energy probes. And that's why we often associate particle physics with being high energy physics, something that's going to happen at these really high energy scales. All right, so I've said the term fundamental particles a couple of times. Let's talk about what those actually are. I really like this little image right here that takes all of the fundamental particles and puts them into a circle and color codes them. So we'll walk through what these are. But the main takeaway of this is that the particles listed in this picture, there's 17 of them. And this is all of the fundamental particles that have ever been observed. This is, as far as we know, everything. And the rest of the universe is just made of these. So there's 4 types of particles here with the 4 different color codes. What we have in red are quarks. These are what's inside of protons and neutrons, and they always exist in bound states, and we'll talk more about that momentarily. Green here are leptons, and this contains the most familiar particle to most of us, which is the electron. So the electron is a lepton, it's down here, and it actually has 2 partners or sort of relatives, which have exactly the same properties as the electron, but higher mass, called the mu and the tau. This side over here, these ones with the little V shape, these are called neutrinos. They're also leptons, but they behave very, very differently. They barely interact. Their interactions are super weak and their masses are super tiny. So they're kind of a fun anomaly, and they're one of the open areas of research in particle physics. So we'll talk about that in a few minutes. Now, what we have here in blue, these are called bosons. This is a special kind of particle because they mediate the interactions between all of the other particles. We refer to them as force carriers because all of the fundamental forces have a boson associated with them that translates that force, except gravity, which we will also talk about. And finally, in black, this is the Higgs boson. This was discovered at CERN in 2012. It is the last missing piece of the standard model that was predicted and then observed, and it gives mass to the other particles. So these 17 together, these are all the fundamental particles that have ever been observed in the lab. Now, I mentioned the forces. Let's talk about those. There are 4 fundamental forces. I'm sure you've seen that before somewhere, but let's walk through them for a moment. So down here in the bottom corner, we have the electromagnetic force. This one's familiar. This is the force we see all the time. This is how we interact with matter, with light. The mediator for the electromagnetic force is the photon. So everything that happens electromagnetically is exchanges of photons. This might sound funny if you're used to electrical current being an electron stream flowing in a wire, but what's making the electrons move is going to be fundamentally photons. So it all comes back to this in the end. Over here, we have the weak force. This is actually mediated by a cluster of bosons, the W's and the Z. And the standard model actually views these two things as united mathematically. On a math level, these are one electroweak force rather than 2 separate forces. Up here, we have the strong force. This one is weird. The mediator for this is the gluon, and we'll talk about it in a moment here. And then the 4th fundamental force is gravity. And this is an interesting exception for us because it is not included in the standard model. So let's talk about the strong force. I said we were going to do that. We can do it right now, and I'll tell you why it's weird. So normal forces, things that you might be used to in everyday life, like electromagnetism, the force between 2 objects goes down as you move those 2 objects apart. Think of playing with a couple of magnets. If you have some magnets and you bring them close together, they feel force from each other really strongly. If you move them far apart, they basically don't interact at all, and you can move them independently. The strong force works the opposite way to that. It's more like a spring. So when you have 2 objects that interact via the strong force really close together, they can move really freely and they basically feel no force. But as you start to pull them apart, they feel a stronger and stronger force as they move apart from each other. So you can't ever really separate them. This results in what we call confinement. All that means is that quarks can't exist alone. They're always found in groups inside of other particles. They're always in composite particles. The terminology here is not really super important. I'm just putting it on the screen to, 1, introduce you to it. So if you go and do some reading about particle physics and you see these terms, you know what we're talking about. And 2, just to kind of give you a sense of what's out there and how all of these things interact with each other. So these composite particles made up of quarks, these are called hadrons. And there's 2 ways that you can build a stable composite particle made of quarks. One way is you can take 1 quark and 1 antiquark. Same thing, but you flip all of the charges, basically. Those 2 bond together and they make a meson. The most common mesons in the world are pions and kaons. We don't tend to encounter them in daily life, but they're around. They get made in the upper atmosphere by cosmic rays hitting the atmosphere, things like that. The other way you can make a stable particle out of quarks is by putting 3 quarks or 3 antiquarks together, and then they make a nice little stable ball called a baryon. And these, the most common baryons, are protons and neutrons. So the nuclei of everything we see around us is actually these. It's these collections of quarks stuck together as baryons. So what is it that we really call the standard model? The mathematical model that describes all these particles and how they all interact with each other is what we would refer to as the standard model. And if you write it in its nice little compact form, you can fit it on a t-shirt. This is the standard model in its most compact form here on the left-hand side. And it looks very nice and clean this way. You can also expand out all of those terms and write the detailed version, and then it looks like this, which is a little less beautiful. But, you know, it contains some terms that you'd be able to get some interesting physics out of. Now, if you're interested in this, I don't know if the slides will be posted somewhere afterwards, but there is an article in Symmetry magazine that you can probably find by looking for the author here that actually walks through all of these different sections of it and what they mean, in case you're curious about seeing that. But what this big messy equation on the left-hand side really does is it describes all of those fundamental particles and all of their interactions mathematically. So it makes predictions, it makes statements about what should be the relative strength of some of these different forces compared to each other, what should be the mass of the W relative to the Z. All of those things are sort of encoded here in the math and are something that's kind of fundamental to building this theoretical model of particle physics. So, okay, well, that sounds great. Looks very complete. So given that we have this beautiful, complicated mathematical model, we have these 17 observed particles, everything seems tidy. Why are there still particle physics researchers? What are we actually doing? it turns out there's a lot left to do. We could think of the goal of particle physics as being to understand the universe through its particles in a consistent and complete mathematical way. We're trying to write the perfect giant equation that tells you how everything works. But how can you be sure when you've understood something entirely? You could write down a bunch of different fancy equations that give you this, but how do you actually know when you're right? What we need is to have a model that is predictive. That is, it makes predictions for things we should be able to go out in the world and measure. And then we need to go measure those things and compare the results and have them match. Our model is pretty good at this. It's even really good at this. But there are some big problems we see that let us know that there's definitely more work to do. So let's take a look at some of those. I'm going to start out with what I would call empirical problems with the standard model. That is, cases where we've measured something or observed something that's directly in tension with the model, and it tells us that there's some kind of problem. So there's a big obvious one you've probably already spotted, which is that, as I mentioned, the standard model doesn't include gravity, and the universe definitely does. So something's the matter there, and eventually we're going to have to figure that out. A second problem with the standard model is that it doesn't explain dark matter. I'm going to come back and give you a slide on dark matter in a few minutes here. But essentially, it's an observed phenomenon in the universe, but not one that's in our math. Third, our model can't account for matter-antimatter asymmetry. To introduce matter-antimatter asymmetry, it's basically that when you look around at the world, everything is made of matter, and we don't see any matter, any antimatter. That doesn't make a huge amount of sense mathematically with our model. I will say here, you can get matter-antimatter asymmetry out of the standard model or out of the models that we have built, but you need something called CP violation, or charge parity violation, which says that if you take a particle, and you swap its charge and you take its mirror image, and then you get exactly the same behavior, that would be charge parity symmetry. If you get different behavior, that would be charge parity violation. And you need a lot of charge parity violation in order to account for why the universe is made of matter. In the standard model, there are some sources that would give you charge parity violation, some mathematical places we know of it, but you don't get nearly enough, not enough to explain the universe that we see. So something's funny there. We know that, but we don't know what it is yet. And the fourth thing I'll mention is the origin of neutrino masses. So I mentioned neutrinos are very, very light leptons. They don't work in the standard model the same way as the other particles. And if you want to get masses for them in the standard model, you basically have to add the masses by hand, which feels kind of weird because for the rest of the particles, the mass just comes out of the math. So that also suggests that maybe there's something going on there we don't quite understand. Now, the next slide I want to show you is what I would think of as artistic problems with the standard model. As in, technically, the universe could work this way, but it feels kind of weird if it does. The first of those is the fine-tuning or hierarchy problem. So to give you an idea of this, the Higgs boson interacts with other particles via these little loop processes. They look like a circle if you draw the interaction happening. And based on our standard model, based on our understanding, the mass of the Higgs boson should be huge, like 10 to the 17 times higher than it is because of these interactions. Instead, it's lighter than the heaviest quark. So why? There are ways you could make this happen mathematically, but they get really awkward and it starts to feel like you're just kind of making things up. The second problem is the strong CP problem. So I mentioned CP, that charge parity violation a moment ago, and I said that there are some sources of it in the standard model. And that's true. All those sources of it in the standard model are to do with the weak force, though. As far as we've ever been able to tell experimentally, we don't see any charge parity violation with the strong force. But mathematically, both of them should be allowed. And in general, it's very weird for something to be allowed but not happening. So the fact that we don't see it seems strange. So we would label this as another big why. So, okay, we've just taken 2 slides to go through a bunch of problems with the standard model. But as you can see, there's enough of them that it really starts to make a person wonder. Now I said I'd do a spotlight on dark matter, just one slide to tell you about it in case it's something that's new to you. This is the idea of having some additional particle in the universe that interacts gravitationally, and that's about all we know about it. but we know it's there gravitationally, because if you look at, say, a spiral galaxy like this one, and you estimate how much mass there should be everywhere from the stars that you can see, you can make a curve of how fast those stars should be moving as a function of their distance from the center of the galaxy. And if stars were all there were in the galaxy, you would get a curve that looks like this. But in practice, we get a curve that looks like this instead. It's very, very different. And the only way that this can align with our understanding of gravity is if there's extra invisible mass in the galaxy. It doesn't emit light, we don't see it, but it has to be there. So that's dark matter. Most of our hypotheses are that this should be some kind of particle. And if that's the case, it's not one of the particles we know. So that's a very interesting hole in the Standard Model. So, okay, we've got all of these problems. How do we go about solving them? Step number one is mathematical work. This is done by our theoretical physics colleagues. So theorists study the problem and come up with possible solutions, essentially mathematical models that could address these, could give you a new particle that does that, or modify a force that does this, and solve the problem. Then the next step is experimental work. So we need to build machines that can measure the properties of particles. And we need to use those machines to search for new particles, to search for new forces, or to do precise measurements of the particles that we know to find any places where their behavior starts to deviate from what the Standard Model tells us they should do. So I think we're just now going to go through, and I'm going to tell you about some of the active areas, the really sort of hot topic areas of particle physics research today. The first one I want to tell you about is neutrinos. So I mentioned that they're very elusive, they're very light, they interact very rarely, but they're very, very interesting. So there's a lot of experiments that are studying them today. Because neutrinos are so tiny, you tend to build very, very big experiments if you want to detect them. If you have a very large volume, you have a higher chance of them interacting. So this is a really great image showing various people in a little tiny rowboat here going around inside of the detector at the Super Kamiokande experiment. So you can get a sense of how big this experiment actually is to catch those neutrinos. Super Kamiokande is studying neutrino oscillation, which is the fact that neutrinos traveling over long distances change types from one type of fundamental neutrino to another, and this can give us information about their masses. Another outstanding question about neutrinos is, are they their own antiparticle? This experiment, which is being built in Canada and Ontario called NEXO, could hopefully answer that question. And potentially my favorite neutrino experiment, studying the production of neutrinos in space by using 1 cubic kilometer of ice with detectors in it. This is the Ice Cube experiment. It is directly on top of the South Pole, and they come out with some very, very interesting measurements of how neutrinos work. The second active area of research that I want to tell you about is precision measurements. So this is what I said momentarily ago, that you can study very carefully how our known particles interact and look for whether or not there's any deviations from mathematical predictions. So one possible question you could study is, do those heavier relatives of electrons, the muon and the tau, do they behave exactly the same way as electrons do? And do measurements of those ratios match the Standard Model? So this is an example of an experiment that's being built right now to do that. The Pioneer experiment will study that question. Another thing you can do is make very precise measurements of the interactions of heavy quarks to try to understand CP violation and look for new physics effects that could tell us where the rest of the antimatter went. The LHCb experiment at CERN is one of the experiments which is dedicated to solving these problems and is really specifically good at these quark measurements. Now, dark matter is also an active area of research today, very specifically, and there's a lot of different experiments that try different ways to measure dark matter particles directly. I'm going to highlight two here that have sort of opposite approaches. So the Super CDMS experiment is building these little hexagonal chunks of germanium. They're about this big, and then cooling them down really, really, really cold and looking for dark matter to interact in there. Xenon collaboration instead takes a big tank of liquid xenon and looks for particle interactions happening in there that could tell you that you've detected some dark matter going through the detector. The goal of both experiments is to try to see the effects of a dark matter particle bouncing off of the nucleus, and the nucleus would react a little bit to having that happen, and that could tell you that you detected dark matter. And then the fourth active area of research I want to highlight today, what we in North America often refer to as the energy frontier. This is high energy exploration and the Higgs boson. So there's only two experiments in the world, the CMS experiment and the ATLAS experiment, both located at the LHC. These are the only experiments in the world that are able to study the Higgs boson because the LHC is the only accelerator in the world that's able to make them. So for this particular kind of work, where you're looking at these really heavy and really rare particles, this is the place to do it. And these experiments make that possible. So my area of research is I work on physics at colliders, very similar to this. So I do experiments at two extremely different particle accelerators that I'm going to tell you a little bit about. The first one is the LHC, that is the Large Hadron Collider. And you can see a picture of it here. You can't actually see it in real life. It's underground, about 100 meters. But this is a drawing of the line on the surface that it would be at if you put it on top of the ground. The location of the LHC, it's in Geneva, Switzerland at the lab called CERN. And this is a circular accelerator that accelerates protons. It's 27 kilometers around, which is pretty far, takes a good amount of time to bike around it. And it accelerates particles to 13.5 tera electron volts. So earlier I mentioned the giga electron volt, 10 to the 9. This actually gets above the scale of 10 to the 12 electron volts, which gives access to some really, really interesting physics at that energy frontier. The other accelerator that I do research at is the aerial ELINAC, this very small accelerator right here. So you can see a beamline kind of hidden away in there in between all of these optics running right to left. This is one of the accelerating units on this accelerator, and then it kind of goes around the corner over there. The location of this accelerator is it's at TRIUMF, the institution where I work here in Vancouver, Canada. This is a linear accelerator, whereas the LHC was circular, and this accelerates electrons where the LHC accelerated protons. It's around 30 meters long, so very different scale from the almost 30 kilometers. And the particle energy that this machine manages to achieve is 30 mega electron volts, so 30 times 10 to the 6 electron volts. That's a factor of 10 to the 6 less than the LHC. I want now to tell you a bit about how collider physics actually works, because it's not super obvious what it is that we're doing. I mentioned energy scales before, and this is very relevant here. So in daily life, in your everyday going about in the world, we only interact with fairly light and fairly stable particles of the Standard Model. I think the ones we would interact with the most are photons coming from the sun. The fact that the nuclei of all of the material around us is made of protons and neutrons, which are in turn made of up and down quarks, the two lightest quarks. We have electrons everywhere, of course, around nuclei making up atoms, traveling in our wires as electricity. We actually have neutrinos passing through us all the time. They come from space, they go through you, they mostly don't interact and they go on their way. But those are around us every day. And we occasionally encounter muons in everyday life as well. These are the next heaviest relative of the electron, and they get created in the upper atmosphere by particles from space that strike the atmosphere and generate showers of particles, and they live long enough to make it to the Earth's surface. So you may or may not have had some muons interact with you at some point coming down from the upper atmosphere. But for our daily life, that's about it. So what do we have to do if we want to study a heavy particle like the Z boson or the Higgs boson? They're not there to be studied. And what if we want to discover new heavy particles, something like that we've never seen before that's similarly really heavy? So the fundamental principles of particle physics all come back to E equals mc squared, an equation that I'm sure you're all very familiar with, but what does it really mean for us? What it really means is that you can take a lot of energy and turn it into a little bit of mass, or you can take a little bit of mass and turn it into a lot of energy. You can sort of convert back and forth between those two things. So if what you start out with is two pretty light particles, like, shall we say, protons, but they're moving really, really fast so that each of them is actually carrying a tremendous amount of energy, and you smash them together, you could turn that into a couple of heavy particles moving very slowly. You're just going from one side of the equation to the other. You're starting with a lot of E and you're ending with a lot of M. So by essentially making these light particles that we have around us every day accelerated to these very high energies, these tera-electron volt energies, we have the chance to generate new heavy particles. Here's what one of these events actually looks like in an LHC experiment. What we did here is take two protons, smash them together really, really fast, and make some heavy particles. In this case, what was made, we think, is a top quark and an anti-top quark. I say here this is a candidate top anti-top event, and we'll come back to that on the next slide. But the interesting thing is you can see those particles then decay immediately and fill the detector with all of this activity. So we've got a couple of very high energy leptons coming out here. This, I guess, would be an electron. This looks like a muon. This is a couple of jets, hadronic things that have quarks inside of them or gluons inside of them. So you make this very, very energetic event. And then you can basically study this as a researcher, break down what you see there, piece it back together and say, well, I know what a top quark decays into, and I can see those items here. So I can put them back together and say, this looks like it was a top anti-top event with this much energy and this much momentum. And then you have something interesting you can actually study to try to understand those heavy particles that were made. Now, so why did I say candidate event as opposed to just event? Why can't we call that a top anti-top collision? Particle physics can only be understood through statistics. You really can't look at an individual event and know for sure what it is. And so to show you what I mean, I'm going to show you a little animation here. In this animation, we're going to look at data collection by the ATLAS experiment from April of 2012, or April of 2011 to the middle of 2012, when the discovery of the Higgs boson was announced. Start out with 0. And as the date progresses, this is the amount of energy we've gathered in weird LHC units. And you can see this distribution of data is slowly starting to climb. Down here, this is the difference between the data and a smooth prediction for the background in blue. And right here, you can see there's actually a really significant difference between those two things. There's our background, which was the blue line. There is in red here a good fit through the data, and there's this significant bump. And the mass of that bump, right around 125 giga electron volts, that's the mass of the Higgs boson. But you can see that it took 2 years between turning the LHC on and collecting all of this data to have enough of a statistically significant statement here that you could say for sure that something was actually happening. And if you were to just grab one of the data points out of this bin and look at it, it's impossible to tell whether that event is actually from a Higgs or whether it's from background that looks like a Higgs. For one event, there's no way to know. But when you put them all together, you can look at the statistics and say that there's definitely something there. So from that idea, I want to move on and just use my last few slides to tell you a bit about what I'm doing. So my research is particularly interested in the question of dark matter, but using colliders to tell us about it. So we tend to assume, because it makes a lot of other things work out well, that there should be some kind of connection between dark matter and the standard model. It's not going to be a direct connection, but there should be something that would let us turn dark matter into standard model particles into dark matter, and so on. And you could kind of draw it like this, as sort of a blob, where I would say this picture represents some kind of interaction between these two things. And this gives us 3 different ways that experimentalists can look for dark matter and do look for dark matter in daily life. So one of these is to look for indirect detection. That's basically, if you read the diagram from the top down, this would be 2 dark matter particles coming together, interacting, and producing standard model particles that you could see with a detector. And so that way of searching for dark matter is something that the ice cube experiment does. You might be sensitive to it in Super K and other big volume experiments like that. If you read this little diagram from the left to the right, then what it's telling you is you could have a dark matter particle come in from space, it scatters off of a standard model particle, and the 2 go in opposite directions. And that bounce back of the standard model particle, that's what those direct detection experiments that we looked at a little earlier are doing, things like Super CDMS, Xenon 1 ton, and so on. But if you read this diagram from the bottom to the top, then what you're trying to do is have 2 standard model particles come together, interact, and produce dark matter. And that's something that we can look for with experiments like ATLAS at the LHC, or like DarkLight and other small experiments at smaller accelerators around the world. So this, I think, comes back interestingly to the idea then of why use different accelerators to do this. I mentioned that I'm doing research at 2 different colliders, and they're both related through this concept of dark matter. My research specifically, I'm not looking for dark matter itself. I'm looking for what makes that blue blob work. There should be some kind of intermediate particle that acts as a connector between standard model and dark matter. And that is something that we can potentially make more easily and study more easily in the lab. There's still a very wide range of masses and a wide range of interaction strengths that this intermediate particle could have that gives us this very broad range that we actually have to look over. So different colliders and different experiments have different advantages and disadvantages for these scenarios. If, for example, the only way to interact with dark matter is through an intermediate particle that's really heavy, then we need that high E to get that high M. And the only place that we would be able to do this is going to be at a very high energy accelerator like the LHC. So ATLAS would be the right tool for the job if nature has given us a very heavy intermediate particle. So the high energy of the LHC makes it really ideal to look for this kind of thing. Another thing that's great is the beams of protons that interact in ATLAS do it right in the middle here. And then we've got detector over almost 360 degrees in every direction around that. So no matter where something goes, you'll be able to detect it. And it turns out that for searchers looking for the production of dark matter, that's super, super useful. So a design like the ATLAS experiment is great for dark matter searches. What if, on the other hand, that particle, either dark matter or the new particle that mediates to dark matter, what if it only interacts with leptons? So what if it interacts with the electron, the muon, the tau, and nothing else? Well, then you don't really want to be using a proton collider to look for that. You would be better off doing a search at an electron collider. Similarly, what if that intermediate particle is actually really light? If that's the case, it's going to be easier to search for it at a beam that's somewhat lower energy, but very high intensity. Something, again, like the linear accelerator at TRIUMF. This is DarkLight. This is the experiment that we are building at TRIUMF to do this search. It has very small angular coverage. So whereas ATLAS had sort of 360 degrees in all directions to look for new physics, this little experiment can basically only search particles that go out 2 little tubes going straight into those blue boxes, and that's about it. So it's very limited in coverage, but as long as we're looking for something very specific and we know where to expect it to be, that should be okay. So what comes next for us? DarkLight is a short-term experiment. We're expecting for it to run for a couple of years, maybe 3 years or something like that, taking data. We haven't started taking data yet, but we're hoping that by the end of this year, we'll be doing that. The LHC has a much longer lifespan. It's a very general purpose, very big facility, and it can run for a long time. So we're expecting the LHC to run until around 2041. But eventually around that time, all of the useful data will be collected. And maybe more importantly, the detectors are not going to live forever. They're dealing with a lot of radiation, and eventually they'll be too damaged to actually give us good signals. So what's next for collider physics after that point? Well, we as a community have a lot of ideas for interesting directions that we could go in next. One of the ideas that's out there on the table is what's called the Future Circular Collider. So if this is another overhead view of Geneva, and you have the LHC here in this blue ring, this indicates what a 100-kilometer long ring could be that could be added to the same location, use CERN as a host lab, but be able to accelerate to way higher energies and possibly be the next step beyond the LHC. Another idea, and one that I think is really very fun, is the cool copper collider idea. This would be for a linear electron accelerator, sort of like the TRIUMF one, but instead of being 30 meters long, it would be maybe 8 kilometers long, and it would be very, very intensive. This is exploring new technologies to be able to accelerate electrons quickly over short amounts of space. And the new technologies that it's using are really the ability to essentially carve copper into incredibly precise shapes that lets you build up this acceleration over really short distances. So this is a really interesting new technology and a fun example of how pushing the sort of fundamentals of the techniques can give you access to new acceleration. And then the last future idea that I want to mention, I think, is actually the wackiest, which is a funny thing to say with the Future Circular Collider on screen. But the wackiest idea out there is a muon collider. So remembering that muons are the next heavy version of a lepton above an electron, what if instead of building an electron collider, you built a muon collider instead? It turns out that you would only need a collider about 10 kilometers around to get you the same physics opportunities that you could get from a 100-kilometer long proton accelerator. The problem is that muons decay really fast, so it's pretty hard to actually build something like this in a practical manner. But people are looking into it, and it could be a really interesting direction to go in for the next discovery machine. So that's all that I have for you today. I'm very happy to take any questions. I believe that will go through the chat or the moderator. But thank you all so much for being here. It's been a real pleasure to talk with you.
Thanks very much, Kate, and I'm sure everyone echoes my thanks for such an interesting talk. I'm an astrophysicist, so I'm only used to looking at dark matter by using telescopes and looking far out into the universe. So it's really interesting to hear about what people are doing here on Earth in order to answer some of these questions. We've had lots of questions in the Q&A section, so I'll just work through some of them. And apologies to anyone who I don't get to their question. I'll do my best to get to as many as possible, but you can post your question on the Nuclear Masterclass forum as well, and it can be answered there if we don't get a chance to get to you today. Okay, so we have a question about whether quantum computers might help us to answer some of the questions around dark matter or things like the Higgs boson.
So it is a very good question, and it is an active area of research. Computing does become a limitation, very interestingly, for some of these high-rate experiments in something like the LHC. So even just looking down the road to the energy and intensity upgrades that we're planning, we're going to run into computational issues trying to reconstruct the data that's coming from millions of channels at once. So some of my colleagues are looking into whether or not quantum computing can offer a way to speed up this and some of the other really computationally intensive processes. I think we're a few years out from it actually being able to be practical in the lab to do this, but the potential is there, and people are exploring it. So yeah, it's a great question.
And have any experiments that are linked to CP violation actually got any closer to learning why there's more matter than antimatter in the universe?
I think it's still a work in progress. You see interesting results come in now and again that might be slightly deviating from the results of other experiments. But so far, the measurements that we've had of it do all sort of indicate that the amount that we're observing in nature is not enough to answer this question. It could be this is a question that will have to be answered from the other side. Theorists could come up with a new mechanism for how you could get matter-antimatter asymmetry that doesn't rely on this. It's just the best idea we have so far.
And why specifically is xenon used for research into dark matter?
It's a useful gas for being ionizable in essentially the properties that you want to have for a particle passing through it to make a signal that you can read out in your detector. It's a very useful type of gas to be able to do that. Argon works as well quite nicely, but argon is less dense. So if you want to increase your rate of reaction for sort of the same amount of material, you go with xenon instead. We keep them in the liquid form rather than gas form, so it's sort of as dense as you can get at very, very ultra cold temperatures. And that sort of gives you that combination of something which is pretty stable, gives you good detection capability, fairly dense. Yeah, and no radioactive background. It doesn't decay, it's very stable.
Great. And so do bosons and other exchange particles also behave like waves as well? And if so, would they not interfere with each other?
Oh, what a fabulous question. Yes. So photons are the classic example of a particle that is both a particle and a wave, depending on what's useful at the moment, the energy scale that you're looking at, whether you squint and it's Thursday. It's sort of the classic experiment for demonstrating particle wave duality is firing photons at a slit and seeing what you get on the other side. And they are a boson. So on that most fundamental level of what we would think of as interference and waves adding and interfering with each other, we see that all the time with photons, which are a boson. So yes. For the others, it's a bit more complicated because other things like Z or W bosons aren't going to live long enough to do something like a double slit experiment with them. They don't sort of propagate over a distance where you would see that. but the interference effects are still there mathematically. So if you sit down to calculate out what should be the interaction rate for something that has these particles in it, they'll still cancel each other out in the math. And what you'll end up seeing in the lab will be a higher or lower rate that you have to essentially take that into account for in order to get. So it's an interesting and complicated thing, yeah.
So do the gaps in the current standard model give any evidence for the existence of particles that we haven't yet discovered?
It's certainly a nice hypothesis. I would say evidence is sort of a hard word for most of this, but in general, I think so, yes. The question really is what energy scale those particles are going to be at. So if there are new particles, but they weigh 1,000,000 tera electron volts, we'll never discover them. They could be out there, but there's not really anything we can do about it. It's really only if they happen to be in an energy range where we're able to access them on Earth or to indirectly quantify them through some other property that's sort of undeniably related that we would be able to say anything more definite in that case. But most theories that suggest ways to extend the standard model to solve these problems, most of those theories will involve some other particle having to be out there. And it's just sort of a question of where and how detectable is it.
And so would dark matter interact with different forces than the forces that normal matter, for example, interacts with?
It certainly could. So I think at this point, it would be safe to say that we know very little about what particle dark matter would look like. We know a few things about it. It has to be pretty stable, can't decay too much, can't interact with light. But the list is quite short. And beyond that, it could be not one particle, but another 17 that only talk to each other. We don't really have too much evidence about what that might actually look like. So there could be a whole dark sector that has their own dark strong force or whatever governing how they interact, and that just doesn't communicate with our forces at all. We're hopeful, again, that there's some kind of connecting link between those. You can build a theory that is self-consistent, where there's simply no interaction between dark matter and the standard model at all. These particles just kind of pop out of the early universe completely independently. But on some level, it's less clean, and a lot of cleaner theories will have some kind of, you just have one family tree for particles, and there should be some kind of interaction there.
And what would a typical day look like for you, Kate, at work?
I wake up early to take a lot of meetings, given the 9 time zone difference from the west coast of Canada to CERN. I spend a lot of time at my computer. So if you're interested in doing particle physics work, a lot of it is computational. A lot of it is software to read out the detectors, calibrate what you see, reconstruct this into events, do the statistical analysis of the events. There's a lot of software and programming involved in this job. I also am lucky that I get to spend quite a bit of time in the lab. DarkLight is still under construction, so we have some very interesting work going on site where the postdocs and students of the UBC and the TRIUMF groups are really leading constructing the trigger detector that we're going to use. So I get to go and see that. So it is a real mix, and every day is a little bit different. But I guess I would say there's more programming than you might guess.
So how would a scientist go about discovering an intermediate particle like the gluon in a detector or elsewhere? So
it's a very good question. It depends on the particle, how you would measure that. Gluons are pretty tricky, so that's maybe the hardest example, because once again, the strong force is pretty weird. But I could take maybe as an example, the kinds of new particles that I'm looking for, something that would be maybe a mediator to dark matter, we would expect it to behave kind of similarly to the standard model Z boson. And for the standard model Z boson, one of the things you can do is predict what it would decay to. All these heavy particles aren't stable. They're going to decay to the light stable particles. And you can predict that from the math of your theory. You can also predict what the distribution of energy and momentum those particles should have would be. So then when you measure a bunch of events, you look for cases where you got results that look like what you think it should look like. And you would basically collect the statistics on that and see if you have some kind of excess. So that little GIF that we looked at with the bump happening where the Higgs was, that's a great example, right? That was the Higgs being discovered because we had a model for what it decayed to. In this case, it was 2 photons. So you would take the 2 photons and you would look at the mass of the particle that could have made them. You put that in this big plot. And if you didn't have the Higgs, it would just be smooth. And if you do have the Higgs, you get a bump. So that's one of the ways you can look for new particles. If they don't decay directly to something you can make a bump out of, it's a little bit harder, but you can still do a similar statistical trick where you would play with what you expect to see without it, what you expect to see with it, take your data and compare the two and see if you see any kind of statistically important difference.
And would there be any advantage to doing some experiments in space instead of on Earth?
It's a very good question. Yes, it depends what you're trying to study. So if you're trying to study the production of particles from events in space, like supernovas, space would be a great place to do that kind of measurement because you don't have all of the interference from the atmosphere in between, which can be very destructive to particles that are coming from space, and then they interact in the atmosphere and they all break up and you don't get much left on the ground. That said, it's pretty hard to do for 2 reasons. Reason number one, if you send something into space, and it's funny to be saying this with someone who does astronomy because you know this very, very well. If you send something into space, you can't repair it. It's just kind of gone. So it's very hard to maintain or develop or improve on something that's really inaccessible. That's kind of challenge number one of the space approach. Challenge number 2 is that space gives you high energy particles. In fact, it gives you higher energy particles than we can make on Earth. The highest energy things we've ever seen were coming from space instead. But you can't control how often they arrive. You can't control where they arrive. It's generally low statistics and pretty random. So if you want to measure that, the easiest way to do it is a really large expanse of detector. So a lot of the Earth-based telescopes that would look for this, you'll have something that covers a square kilometer with measurement devices, and you can't really put that in space because it's too hard to fly around. So if you need something that covers a lot of space, it's easier to put it on Earth. The advantage of a particle collider is that you're not waiting for space to deliver your high energy particles. You make them on demand right where you want them, and you put them in a very specific spot, and then your detector just needs to surround that spot. So it's a bit of a statistics game. There is one experiment called AMS, and I can't remember what it stands for, but it does some similar work to CMS, and it's actually based on the International Space Station, and it's looking at stuff from space. So that's a fun example if you want to check one out.
Great. And okay, I'll move on to the final question. Do you have any books or articles or documentaries that you'd recommend to anyone that wants to learn more about these topics?
Oh, let's see. So books, in terms of sort of science outreach or sort of popular accessible science level books, I'm a fan of John Butterworth's books. I think he writes some really nice things. He's at UCL, if I'm remembering correctly, and writes about CERN and sort of high energy physics. I'll also say, I don't know where you can find it these days, but there is a lovely documentary called Particle Fever that was made a few years after the Higgs discovery by some of the theorists who were sort of involved in that. And I've never seen anything else that captures quite as clearly what the day-to-day experience of doing this kind of work is actually like, and what sort of the excitement of that time was like. So if you're interested in seeing people at CERN messing around doing the work that they do to make this data come together, I would recommend finding Particle Fever. I do think it's really fun. You can also see a great clip of 2 of my friends asleep in the Higgs discovery announcement in it.
Oh, amazing. I'm going to throw in one more, if that's okay. Sure. Just in terms of what would you recommend that people study at school in order to get into this field of research?
Physics is the big one. I'm sure you have the chance to do physics at school, wherever you are. The other really important things, math is obviously the basis of everything that we do, and it's very foundational to a physics degree. The 2 that you probably don't need to worry about at this point, but if you get the opportunity to take these when you get to university, statistics is really relevant to a lot of what we do and is often not actually a required part of a physics degree, but is very useful, and then programming. So learn to code.
Brilliant. Well, thank you very much, Kate. And yeah, for both a very interesting talk and giving such comprehensive answers to the many questions that I've just thrown at you.
Thank you.
But
And thank you all for being here and for asking such great questions. It's been really fun to get to chat with you today.
great. And yeah, so for anyone watching, the recording of the event will be made available on the Nuclear Masterclass website later in this week or early next week. And a link will also be emailed to all ticket holders. So yeah, thank you everyone for joining us this evening. I hope you have a pleasant evening. And I know, Kate, for you, it's actually morning. So I hope you enjoy the rest of your full day at work.
Thank you so much. Thanks, Josie. And thanks, everybody.
Bye.
Bye.